Hi everyone, Matthew's back at Shaw Engineering, and welcome to the first episode in the series where I will be breaking down every component of a 3D printed compressed air engine. Today we're looking at one of the most important critical parts of the engine, the piston. The piston job is very simple. It converts the pressure of the compressed air into linear motion. As compressed air enters the cylinder chamber, the pressure acts on the piston's face, generating a force equal to the air pressure multiplied by the piston's surface area. This force drives the piston along the cylinder, which then rotates the crankshaft throughout the connecting rod. The performance of the entire engine depends heavily on how well the piston seals against the cylinder while keeping as low as friction as possible. Let's look at the most common piston designs. So first of all, the simplest design is a square or rectangular piston printed as part of the engine. Because it has flat faces, this design is easy to model and print without requiring precise circular dimensions. It also has a large contact area, making it resistant to rocking inside the cylinder. However, from an engineering perspective, it's one of the least efficient designs you can put in a miniature 3D printed engine. The sharp corners produce very high contact pressure, including sliding friction. Since FDM 3D printing leaves small layer ridges, these corners tend to scrape against the cylinder walls rather than gliding over them. Air sealing is also very poor. Small dimensional errors caused by printer tolerances, material shrinkage, or thermal expansion creates leakages paths around the corners. Because compressed air follows the path of least resistance, even a gap of a few 0.1 of a millimeter can dramatically reduce efficiency. Another issue is uneven wear. The corners experience most of the contact force, causing them to wear much faster than the rest of the piston. As the corners wear, air leakage increases and the performance of the engine gradually decreases over time. Overall, this design is suitable for a proof of concept engine and engines that you're starting off with, so it's a very good engine to start off with if you don't have much machinery to create very high dimensions, as the piston's square, you can file down or sand the edges until it fits very well, making it a very simple first engine piston design. But it's really used in high performance miniature engines like these ones we have over here. The next step is the conventional cylindrical piston. A circular piston distributes side loads evenly around the entire circumference, reducing local pressure and allowing the piston to move much smoother inside the bore. Unlike the square piston, there are no sharp edges dragging against the cylinder wall, so friction is significantly lower. A piston cannot tightly fit inside the cylinder because it will seize as the material expands with temperature or absorbs moisture if the material is porous. Instead, a small running clearance is required. If the clearance is too small, friction increases and the piston may jam. If the clearance is too large, compressed air can escape around the piston, reducing power. For small 3D printed engines, typical running clearances are around 0.05 of a millimeter to 0.15 millimeter, depending on your printer's accuracy, material, and surface finish. Surface finish also plays a major role. Layer lines increase friction, so many builders sand polish or reamer the inside of the cylinder after printing to create a smoother bore. Next, we have an O-ring sealed piston. A much more efficient solution is adding an O-ring. A groove is machined or printed, but most of the time printed, around the piston, allowing the elastomer O-ring to sit slightly proud of the piston's diameter. When compressed air enters the cylinder, pressure pulls the O-ring outwards the cylinder wall, improving the seal even further. This dramatically reduces blow-by, the leakage of compressed air around the piston, which means much greater percentage of air supplied is converted into useful work via pushing the piston down and converting it into rotational motion. However, every improvement comes with a trade-off. The O-ring increases sliding friction because the rubber continuously contacts the cylinder wall. The groove dimensions are also critical. If the groove is too deep, O-ring won't seal properly, but if the groove is too shallow where the O-ring sits, excessive friction, and accelerate wear. Lubrication is usually recommended because it reduces friction, improves sealing, and extends O-ring life. Like with every engine, you have to use oil, but I'll be making a custom video about what oil you should use for different types of engines. Overall, O-rings provide one of the best compromises between efficiency, reliability, and ease of manufacturing. Though, if they are not properly designed, what can happen is the cylinder can start rocking inside the bore, wearing out the bore or losing a lot of compression and increasing a lot of friction. So it's very important that your piston, like I have on this one over here, I have this seal that we'll be talking about later, and then the piston, this piston wall doesn't rock in it, but it still allows it to slide without much friction. Next we have my favorite design by far, and almost all of these engines are using these designs. We have this engine, this is my first with this type of design, then we have this one, this is my last one, and then we have the second one, which I also built with a very similar design with all of them. Okay, one of the most effective piston seals for a miniature compressed air engine is a flexible sealing flange. If you watch Tom Stanton's videos on air engine, you could see that he made a silicone mold off a resin printer and then poured silicone. It took him many tries. Instead of sealing with a round O-ring, a thin rubber lip contacts the cylinder wall like Tom Stanton did. When compressed air acts on the rear of the flange, the lip expands outwards. The higher the air pressure, the harder the seal presses against the wall. This is known as pressure-assisted seal. Because only the thin edge of the flange contacts the cylinder, friction remains surprisingly low while maintaining an excellent seal. This is why Lego pneumatic pistons work so well, and I'll be making a whole video on how I make them. The rubber sealing cup is manufactured with extremely tight tolerances and is made from a material specifically designed for repeated low friction motion for hobby engineers building very small engines. Reusing these seals and DIYing them to your own piston 3D printed designs can produce an excellent compression without requiring precision machinery. The main disadvantage is manufacturing. Producing custom rubber flanges requires molding flexible materials with accurate dimensions, making them much more difficult to produce than a simple 3D printed piston or an O-ring design. Though, if you did buy this Lego, I just bought these from AliExpress. What I do is I just cut off this little metal bit and then literally glue on with a glue that does not deteriorate in oil onto this piston which guides the cylinder. This is what I did with most of them, excluding these two engines which I'll talk about later. So that does it for all the piston designs. They're negatives and positives all about them. So yes, we'll talk about which design is the best for you. Each design has its place. A square piston is quick to print and ideal for testing concepts, or if you're a beginner and don't have much machinery in your house. Let's say you just live in an apartment and you just have a 3D printer, some sandpaper, some files and some screwdrivers. A cylindrical piston would be quite difficult to make, as you'd have to have a resin printer to make a very accurate one, or if you're using a 3D printer you'd have to sand it until the tolerances are really nice, so you get a lot of power and a good compression, but it is quite hard to do. So the easiest way is to use a square piston, as you can sand down the edges until it's the perfect tolerances. As it's not cylindrical, it's a lot harder to do with sandpaper because you can make it oval. But if you do have access to a lathe, what I did with this engine over here is I used a syringe cylinder, so literally from a syringe over here. And then here is a Petri piston. Now the reason I used syringe is because the syringe is actually a very thin material and it's a little bit flexible. So when it heats up, it kind of produces a bit of a better seal around the piston and with making the efficiency a lot better. But overall, this engine has almost no flow. It's very little friction. Like compared to this engine over here, oh, it's a heavy boy. This one is a bit tighter, but it does have a lot better compression. This one does run smoother, but that one is a lot more powerful. So, and these pistons, what was I going to say? These pistons I made on the lathe actually. So I took these pistons, I put them to the right diameter on the lathe, and then I just cut them off and put them in there, and that works very well. But if you don't have access to a lathe, it is a bit trickier to make an efficient and powerful design with a cylindrical piston. Though the cylindrical piston does offer low friction compared to the square one and smoother operation, as I said, it requires a lot more tolerances. Now next is an O-ring piston. An O-ring piston is a very good choice, but I've never used them because I don't know, I just never got my mind up to using them. An O-ring piston provides excellent sealing and significantly improves efficiency compared to the square one and the cylindrical one if you do the O-rings right, making one of the most common choices for hobby compressed air engines around other people for high performance ones. So I wouldn't say I highly recommend the O-ring one, but I've never done it. So I can't exactly say my opinion about the O-ring one. If you watch some other videos, I think Tom Stanton did one, and another guy did one also. They have a few videos on their sealing. But what I don't like about the O-ring is that if you don't get it right, the piston can start rocking a lot. And then what happens is if it rocks, let's say this way, the angle increases. So what happens, the diameter actually increases of the piston inside the bore when it's on an angle. So that increases very high friction. So it's hard to keep the cylinder straight with an O-ring because it's a small curved face. And also what I like about the O-ring is, yes, it does actually, when you put compressed air into it, if you look in Tom Stanton's video, the O-ring does actually expand a little bit, but it expands just from the compressed air. It doesn't physically, it's not meant to physically expand. But with this flange, you see it has these tiny little grooves over here. I don't know if you can see it properly, but it has these tiny little grooves, and it changes between pressure. Let's say you have 20 psi inside your cylinder. What happens is the flanges don't come out all the way like in 60 psi. They just come out a little bit to support that 20 psi, making it perfect. So let's say you have a tight O-ring. A tight O-ring only meant to run at 60 psi. And then, so that means if you have a tight O-ring that's meant to run at 60 psi, or a loose O-ring that's meant to run at 60 psi, you can't be able to run it at those lower pressures or those higher pressures. But with this type of piston design, you can literally run at any pressure until it explodes. Okay, so finally, a rubber flange or a Lego pneumatic seal provides outstanding sealing with remarkably low friction. It's what I use in all my high performance air engines, making it one of the best options for miniature engines where every bit of efficiency matters. In the next episode, we'll move on to talking about the crankshaft mechanism and the con rods. Over here we have this, and how to design this, and all about the different designs of doing them. So you see I'm actually quite experienced with them. So we have these, I've made these quite complex over here with this, my latest engine, quite a complex. This is based off a ship. So that's what we'll be discussing about in the later video. Thank you for watching. Don't forget to like and subscribe to support my channel. I would really like that because I really like to make these videos and continue making them for you. So thank you very much, and bye.